Hello and welcome back to MEC 416/816 Engineering Acoustics. In this lecture, we're going to continue our discussion of elastic waves, and we're going to focus on the axial vibration of a bar, and we're going to derive the wave equation for that system. So I've drawn here an axial bar, and in this case, we're considering motion axially along this bar. So I'm just drawing with the laser. We're thinking about motion along that. So you can think of a wave coming and propagating down, maybe hitting the boundary, then reflecting back off that, and then bouncing back and forth. That's the kind of motion we're thinking of in this problem. So in this case, we're going to measure the axial displacement using u of x comma t. So previously used v in the string, now we're going to just use u instead. And we're going to consider an applied force. This will be acting axially along the bar. We'll just call this f of x comma t. Then the bar is going to have some properties, an elastic modulus E of x, a density rho of x, and a cross-sectional area A of x. The rod or bar has a length of L, and again that horizontal direction is x. And one thing I'd just like you to note is that m of x, the mass per unit length, is simply equal to rho of x times A of x. Okay, we're going to consider now a differential element. I've gone ahead and drawn it here. We'll say that this has a length of dx. And then on the right here, we've drawn a zoomed in view of that. So first, we have our axially applied force acting on this element. That's our f of x comma t. Our displacement up to the left end is u of x comma t, and then up to this right end is u of x plus dx comma t. We're then going to have a normal force acting on the left hand. We'll call that n of x comma t. And a reactionary normal force acting on the right hand side, which will be n of x plus dx comma t. Okay, at this point we're going to make some assumptions, and then we're going to convert that normal force into something that depends on the parameters of the system, and then we will end up doing a force balance and applying Newton's second law. Okay, so first we're going to assume that the material is elastic and there are small axial oscillations. This is equivalent to saying small displacements. What that then tells us is that the strain, which we can say is epsilon x comma t, and let me just label this. So this is our strain. The strain is then going to be equal to partial u over partial x, or u sub x. What this then tells us is that the stress, we'll say sigma of x comma t, is equal to E of x times the strain epsilon of x comma t, such that we find that the stress x comma t, so the stress here is sigma of x comma t. This must be equal to E of x times u sub x. Okay, so the local axial force acting at x is that normal force n of x comma t, and then that's equal to the stress at that position, sigma of x comma t, multiplied by the area at that position. such that we find that n of x comma t must be equal to, bringing in the relationship equation 13, we'll find that it must be e of x times a x times u sub x. And u sub x is a function of x and t. And just so we note here, we wrote it above, but in my original notes I had it here, that partial u partial x is equal to u sub x. So we'll just add that in for completeness. So we're then going to move to the right by dx along that reference axis x, and then by infinitesimal continuum mechanics we can write that n of x plus dx, let me rewrite that, dx comma t, this is equal to e of x plus dx times a of x plus dx times u sub x of x plus dx comma t. It's the same as like what we had previously, except now that we've incorporated that dx term. We now apply a balance of forces to the system, starting with the mass times acceleration, which will be m of x dx times u sub tt, that's the second partial derivative of u with respect to t, is then equal to n of x plus dx comma t minus n of x comma t plus f of x comma t dx. Okay, so you can apply the same procedure as what we did for the string by expanding with the Taylor series, and doing so we'll end up with the following. We'll end up with m of x times u tt is equal to the quantity e of x times a of x times u sub x, all of that with a subscript of x, meaning that we're taking a derivative with respect to x of everything inside the square brackets, plus f of x comma t, valid for 0 less than equal to x, which is n less than equal to l, and t greater than or equal to 0. And that is the wave equation for an axial bar. Oof, let me draw a better square than that. I'm just going to move this down a little bit so I can then draw a square. There. Okay, so we can now look at initial conditions. In fact, actually, I think for another mini homework, again, this will just be 5 points. And we'll make it due on, let's say, February 6th as well, just like the first mini homework. February 6th, 2024. For this mini homework, I'd like you to show that equation 18 is obtained from equation 17 by applying a Taylor series expansion like we did for this string. So in February 6, you should turn in by hand on a piece of paper for mini homework 1 and now mini homework 2 as well. Alright, so for initial conditions, it's going to be very much like the string, except we're going to be using u. So we'll say u of x comma 0. We'll just say this is equal to some function w1 of x. And then for the velocity, we'll have u sub t of x comma 0 is equal to, in this case, we'll just say w2 of x. And these are two generic functions that are defined for the entire bar. Okay, we're now going to go through boundary conditions. And here we're going to go through both the two simple boundary conditions, a free and fixed end, and then we're going to look at two non-simple boundary conditions, which will be a stiffness and a mass at the boundary. Okay, so for a fixed end, it's going to be very much the same as what we saw for the string. So we'll just write it out at x equals 0. We will get that u of 0 comma t is simply equal to 0. So no displacement there. At x equals L, we'll get u of L comma t is equal to 0. Now for a free end, it's going to be similar to what we saw before. Although, however, this one is actually going to be a little bit more complicated. So we're just going to write here at x equals 0. In fact, let's just simplify 0 comma L. So either of these, we will have that the limit as x approaches 0 or L, the quantity EA or E of x times A of x times u sub x of x comma t, that is equal to 0. It's the limit that is equal to 0. Now, if E times A does not equal 0 at either of these limits, then you end up with exactly what we had for the string. However, you can see I've drawn this kind of triangular rod. In this kind of case, this is a case where you would have to apply the limits. So here we would say at x equals L, we will clearly have to do the limit here. So for the string, we could never have this kind of geometry that goes to 0 because the string has no width to it. We assume that it had infinitesimally small width or thickness. However, the axial rod or bar does have some non-zero thickness, and as a result, it can have geometry that goes to 0. And so we have to take that into account when we apply the boundary conditions. Okay, let's now take a look at a stiffness boundary condition. This is where you have a discrete spring applied to the structure at a particular location. I've drawn a picture here. You're going to go through a worksheet in class where you'll see how we derive this. This will be the first worksheet we do in the class on the first day that we're actually meeting in person. However, in this case, we're looking at a spring applied to the position x equals 0. We're then going to perform a balance at x equals 0 plus. And just as an aside here, when we say 0 plus, what we mean is 0 plus some very small number, which we'll say epsilon, and epsilon here is much less than 1. So it's just a little bit more than 0. And then we would end up taking a limit as that epsilon goes to 0. Okay, but doing so results in the following. We'll get that for x equals 0, we get that E of 0 times A of 0 times u sub x of 0 comma t, that is equal to k times u of 0 comma t, so that's the displacement there. And then similarly for x equals L, we will get that E of L times A of L times u sub x of L comma t is equal to minus k times u of L comma t. And just for reference, the spring on the other side would look something like this. Okay, the last boundary condition we have to deal with here, and I apologize for any noise that you might have heard there. The last boundary condition we're going to deal with is the mass m, and in this case, you'll see this in class when you do the worksheet, so I'm just going to write out what the boundary condition is. We get here that e of 0, this is for x equals 0, the one below here is x equals L. We get e of 0 times a of 0 times u sub x of 0 comma t. This is equal to that mass times u sub tt at 0 comma t. That's acceleration at that point. And then on the other side, we'll get e of L times a of L times u sub x of L comma t, then equal to, in this case, minus m u tt times of L comma t. And that is the boundary conditions for a bar undergoing axial oscillations. In the next section, we're going to cover the general solution of the wave equation and show how traveling waves are formed.